Hello everyone. In this video, I'm going to walk you through some of the R codes to implement nonlinear methods of statistical learning. So I'm going to download some libraries. I'm going to use data from the SLR2 package. I need this package for some plotting purposes, and we're going to work with the wage data. So everything is loaded. So first up, we are going to plot polynomials of degree 4. The easiest and the most recommended way of doing it is using the ln function and then using the poly function within that. So this command will generate a regression where you have age, age squared, age cubed, and age to the power 4. So run the regressions and you get the point estimates. There are other ways of doing it as well. You can separately create these polynomials and then run the regression. They are all the same, but my vote would be to use the poly function. For next, what I'm going to do is I'm going to create a grid of ages for prediction and plotting purposes, and I'm going to create a sequence over here from minimum value of age to maximum, and then I'm going to predict the value of the dependent variable from the polynomial function. And I'm also going to compute the standard errors and then plot the data. As you can see, this is a fourth order polynomial over here. I can also run I can also do it in the context of a logistic regression. And so instead of GLM, we will use GLM, and I will have a dummy as my dependent variable that will take the value 1 if the wage is over 250, 0 otherwise, and then fit the model. Get the predictions, do the transformation from log odds to odds ratio, calculate the standard error, transform the confidence interval as well, that's also important. Or a straightforward way of doing it is using the predict function. And this is on this. So this is for the linear function, this is for the binomial, like logistic regression. As you can see that the probability that the person earns more than 250,000 is highest around this age, and then it declines. And the dotted lines over here plot the confidence intervals. The standard confidence intervals are larger over here is because there are too few observations in this interval. Then doing a step function is pretty straightforward. You just have to use a separate function table and cut. That will cut the age variable at 4 different points and then fit a regression model. So instead of fitting a continuous predicted age, I'm providing 4 cuts. So there are three levels: 33 to 0.5 to 49, 49 to 64.5, 64.5 to 80.1. Because when I'm using dummies, one group has to be kept as reference. To do the splines, we use package splines, which has the function. The difference is that we use the lm function, but then instead of writing the age directly, we use the bs function, put in the variable against which we want to cut, and then specify the knots. So in this line, I'm running a regression with splines where the knots are at 25, 40, and 60. And then I'm predicting and then plotting the lines. And we have a figure. to use the natural spline. Again, instead of BS, we are using the command NS, where NS stands for natural spline. So you see the biggest advantage here is that you don't have to do any of these manually. R has packages that have built-in functions to let you do this stuff. You just need to understand what you're doing and what you're getting. And the red line over here plots the natural spline over the regular spline. As you can see over here, areas where there are a lot of data points, the natural spline and the normal cubic spline, they are very, very similar to each other. They start differing in areas where there are very few data points, that is at the boundary. And that's because from theory we know that natural spline assumes at the boundary handles few observations much better. So it doesn't try to draw too much information, like draw too much conclusions from too little information. Smoothing splines take a different approach. So where is the code for the smoothing spline? Yes, smoothing spline takes a different approach. It places knots at every unique value of x and controls the flexibility through a penalty term. And if you want to add cross-validation to it, you need to just write CB equals true. Then it will select the knots using cross-validation. And the optimal degrees of freedom is 6.74, which is roughly 7. And we can compare these plots using these lines of code. And as you can see, the blue shaded area is that for the smoothing spline with cross-validation, and the first one is with 16 degrees of freedom. So obviously, since we are allowing for cross-validation to pick the best result, our prediction using the cross-validation is much better because we have narrower confidence intervals to work with. Then we do local regressions. So the command for local regressions is lowest. We write the function, we specify the dependent variable, independent variable, specify the span, and write out which data to choose from. And sorry, this is that figure. And last, we have the generalized additive models. For that, we need the GAM library and then the GAM function. So what we're doing is that we're fitting splines over here with respect to year and age, and education is added as separately. So as you can see, since we're allowing for each predictor to have a separate relationship between that and the predictor, like the response variable, we are getting different associations. We have different predictions. For year and age, we are assuming smoothing splines, but for education, we are having like a regression where we have like a regression for different values of education categories. The rest of it is extra. It's not super essential for this course, but I've still kept it so that it gives you an opportunity to work through. And that's about it. Here, so the key thing over here is not the R codes, because all the functions that you're going to use are already there. More important for you is to understand what you're doing and then make sure you have the right intentions and you are aware of the limitations and pros and cons and you are using the right method for the right data. That's about it.